A necessary and a sufficient condition for a n solutions y1, y2 and so on yn of dn y upon dxn plus a1x dn minus 1 y dxn minus 1 plus so on plus anx y equals to 0, where a1, a2 and an are the continuous on closed interval ab to be linearly independent, is that the value of the Wronskian W y1, y2 and so on yn does not equal to 0 for all values of x belongs to closed interval ab. Proof. Necessary condition: let y1, y2 and so on yn be the linearly independent on closed interval on a is less than equal to of x is less than equal to of b. We are to prove that y w y1 y2 and so yn x does not equal to 0 on closed interval a is less than equal to of x is less than equal to of b. Let x0 be the point on a is less than equal to of x is less than equal to of b, such that w y1 y2 and so on yn x0 equals to 0. Equation 1, which implies that the system of n linear equations c1 y1 x0 plus c2 y2 x0 plus so on cn yn x0 equals to 0. c1 y1 dash x0 plus c2 y2 dash x0 plus so on plus cn yn dash x0 equals to 0. c1 y1 n minus 1 x0 plus c2 y2 n minus 1 x0 plus so on cn yn n minus 1 x0 equals to 0. Equation 2 has a solution c1 c2 and so on cn where not all the constants c1 c2 and so on cn are 0. Let c1 c2 and cn be such a solution and are considered the function phi equal to c1 y1x plus c2 y2x plus so on cn ynx. Equation 3, since y1x y2x and so on ynx are solutions of the given homogeneous linear differential equation, therefore phi is given by equation 3 is also a solution of the given homogeneous linear differential equation. Therefore L phi equals to 0. Equation 4, from 2 we see that phi x0 equals to 0, phi dash x0 equals to 0 and phi so on phi n minus 1 x0 equals to 0. Therefore from the theorem let x0 be a 1 and let alpha 1 and so on alpha n be the n constants. Therefore at most there is at most one solution of phi of Ly equals to 0 on I satisfying as phi x0 equals to alpha 1, phi dash x0 equals to alpha 2 and phi n minus 1th derivative of x0 is alpha n. It follows that phi x is 0 for all x on a is less than equal to of x is less than equal to of b, which implies c1 y1x plus c2 y2x plus so on plus cn y and x is 0 for all x on a is less than equal to of x is less than equal to of b. But this contradicts the fact that y1, y2 and so on, yn are linearly independent on a is less than equal to of x is less than equal to of b. Therefore, the suppositions that there is a point x0 in a is less than equal to of x is less than equal to of b such that w, y1, y2 and so on, yn x0 equals to 0 is false. Thus w, y1, y2 and so on, yn x0 does not equal to 0 for all x on a is less than equal to of x is less than equal to of b. The sufficient condition suppose that w, y1, y2 and so on, yn does not equal to 0 for all x on a is less than equal to of x is less than equal to of b if there are constants c1, c2 and cn such that c1 y1 x plus c2 y2 x so on cn yn x is 0 for all x on a is less than equal to x is less than equal to b. Equation 5. Also c1 y1 dash first derivative of y1 x plus c2 y2's first derivative plus so on cn y and first derivative x y first derivative of y and x equals to 0 and c1 y1 double dash x plus c2 y2 double dash x plus so on cn y n double dash x is 0 equals to 0 c1 y1 n minus 1 x c2 y2 n minus 1 x plus so on cn yn n minus 1 is the derivative of x y and x equals to 0 for all a is less than equal to of x is less than equal to b. Equation 6. For a fixed x in a is less than equal to of x is less than equal to b, the equation 5 and 6 are n linear homogeneous equations satisfied by c1, c2 and so on cn. The determinant of the coefficients is w, y1, y2 and yn x, which is also a non-zero. Hence there is only one solution to this system, namely c1 equals to c2 equals to so on cn equals to 0. Therefore y1, y2 and so on are linearly independent.